Okay, and I hope you liked that little joke that we had in the beginning. I just pulled that off the internet. I thought it was funny, little icebreaker to start the video. But what you're looking at right here is the Python code I wrote to explain the concepts visually, kinda, of the central limit theorem, standard deviation, that I'd like to go through. And I'll be sure to upload this in the YouTube comments and give it to my professor to hand out if he does show this video in class or whatnot. But if you know Python, feel free to manipulate the code any way you want. I just made it as simple as I can. I wrote a little bit about standard deviation in here in the code, a little bit in the central limit theorem right here, and then here's the main part of the code for the GUI. I felt it was important to make a GUI just to visually show, and I think it nails home concepts a little better. But standard deviation, let's talk about that real quick. The standard deviation, it's important. Well, actually, it's the Greek letter sigma. It's usually represented by, and it's the measure that is used to quantify the amount of variation or dispersion of a set of data values, which means, say a bunch of test scores, you want to know what the average was, and you want to know like the best score, how far ahead of it was it. It'll give you a better idea of how much better students are doing, how far they lie within the average, above the average, things like that. And it's important, well, for that very reason that I discussed. But basically, the standard deviation, you've heard of 1 sigma, 2 sigma, 3 sigmas ahead of. Well, basically, there's a 68, 95, 99, 7 rule, which is shorthand to remember the percentages of the values. So say the average test score was 50%, and you scored 100%. You would be about 3 sigma, 99%, which, well, let me explain it this way. 68% of all the scores, here's your mean, here's your average right here. And then 68% of all the scores of data you will gather will lie within 1 sigma. 2 sigmas, 95% of all the scores will be represented in here. 3 sigma, 99%. So your hundreds. If the average was a 50, your hundreds, or your zeros. If someone didn't show up, they were 3 sigmas in a bad way. So let's run the code, and let's take a look at, here we go. Let's take a look at standard deviation. Now let's choose a value range that we want to pull from. So let's say we want to go from 0 to 100. And how many times would we like to pull, randomly draw the values? Let's say we want to do it 1,000 times. And if you look over here to the right, what happened was from 0 to 100, the range you have chosen is 0 to 100. You have chosen a sample from this range 1,000 times. The values chosen are, and all of these were randomly chosen one at a time and stored. And then the mean of the numbers is 48. Really close to 50, what we would expect. And so what that shows us is if we took it 1,000 times, 48, the variance is 840, then one standard deviation from the mean is 28.98. So 68% of all the values will be in this range above or below 48, which makes sense. Now let's see if we run it again and we can get closer to 50, which will bring us into our next topic, the central limit theorem. Kind of lead us into it. Let's do 0 to 100, but let's do another 0. Let's do 10,000 and see if that improves. We want to see the mean be at 50. That would be, a pretty more exact answer. So here we go. 49. Got a little closer. But see, the standard deviation stayed about the same. That's going to be common because about 68% of all the values are going to be within this number halfway through. So, that does make sense. And the reason I was saying let's lead this into the next topic is because we do have the central limit theorem. Now, the central limit theorem and why it's so important is we want to be able to take a set of data and get a normal distribution, which would be like this. Because when we have the mean, And we have this function. We know all about our data, and the central limit theorem says that if sufficient amount enough pools are taken, well, let's put it in words right here. These are better. In probability theory, the central limit theorem states that given certain conditions, the arithmetic mean of a sufficiently large number of iterates of independent random variables, each with a well-defined expected value and well-defined variance, will be approximately normally distributed regardless of the underlying distribution. That means no matter what kind of data we're taking it from, if we take sufficient enough of randomly amount of pools, we will see a normal distribution start to take form, and that is what we want when we want to represent data, because a normal distribution represents 100% of all our values under a bell curve. Now, let's try and put this in perspective. So this is hard-coded. The samples will be taken from a value range of 1 to 10. Okay, so let's input the sample size. Let's just start off with a sample size of 5. From 1 to 10, how many times are we going to do it? Let's do it 10 times. It's crap. Doesn't tell us anything. I mean, I couldn't tell you what the mean I couldn't tell you anything about this data, okay? So the central limit theorem says, let's take more sample sizes and more times pulling it, and we should start to see a normal distribution. So let's do, let me close this. Let's do 20, or actually let's do 15. Let's do it 100 times. Okay, it's looking a lot closer. Now we're seeing about 3.5 to 6.5. Couldn't really tell you the mean it's saying is probably somewhere in here. I couldn't tell you exactly, but let's see. Let's go up a little further. 30 is what they say is normal. Let's do 1,000 times. This should give us something more reasonable to work with. Okay. So we're from 3.5 to 6.6, 6.5, and we're seeing a closer to the real mean that we should expect, and a better normal distribution looking. So let's do it 10,000 times, and let's do 50 for the kicks of it. That's what we want to see right there. From 4 to 6, very well defined. 5, I know, boom. Got even amount going on the other sides. This is looking like a very nice normal distribution. And the central limit has proven once again to be right that if we take enough input, or if we take enough sample sizes enough times, that no matter the underlying data set, we will be able to see a normal distribution take place for our data. And like I said, that's all I got for now. I hope that helped. And if not, go to your office hours. That's why they're there. They want to help you, I promise you. But if not, I'll do a quick roll through of this code. You can write it line for line, copy, paste. Feel free to mess around with it, do whatever you want with it. I made it for you guys, made it for this video. But yeah, I hope that helped, and I don't really know how to end these videos, but have a good one. It was a pleasure, and I'll talk to you soon.